One small step added, one big idea revealed, numbers grow, carries travel, and logic quietly prevails. Welcome to this presentation on the problem titled Plus One. In this session, we will explore how a simple operation uncovers elegant problem solving techniques using arrays and careful reasoning. We are given a large integer represented as an array called digits. Each element of the array corresponds to a single digit of the number. The digits are ordered from the most significant digit on the left to the least significant digit on the right, and there are no leading zeros. Our task is simple in theory. Increment this number by 1 and return the resulting array. However, we must do this without converting the array into an integer, since the number can be very large. Let us start with a simple example. The input array is 1, 2, 3. This represents the number 1, 2, 3. When we increment 1, 2, 3 by 1, we get 1, 2, 4. Since there is no carry involved, only the last digit changes, therefore the output becomes 1, 2, 4. This is the most straightforward scenario. Now consider a slightly more complex example, 4, 3, 2, 9. The last digit is 9. When we add 1 to 9, it becomes 10. We write 0 in the current position and carry 1 to the left. That carry is added to the previous digit, turning 2 into 3. The remaining digits stay the same. As a result, the final output becomes 4, 3, 3, 0. This slide shows the most important edge case. The input is 9, 9, 9. Each digit becomes 0 when we add 1 and the carry keeps propagating to the left. After processing all digits, we still have an extra carry remaining. To handle this, we insert a 1 at the beginning of the array. The final result becomes 1, 0, 0, 0. From the examples, we can make a few key observations. Addition always starts from the rightmost digit, just like normal arithmetic. Carry propagates toward the left. The moment we encounter a digit that is less than 9, we can increment it and stop. Only when all digits are 9, we need to increase the size of the array by adding a new leading one. Based on these observations, our algorithm is straightforward. We traverse the array from right to left. If the current digit is less than 9, we increment it and immediately return the array. If the digit is 9, we set it to 0 and continue moving left. If we finish the loop without returning, it means all digits were 9, so we insert a 1 at the front of the array. Here we see the C++ implementation of the algorithm. We loop from the last index to the first. If a digit is less than 9, we increment it and return the result. Otherwise, we set the digit to 0 and continue. After the loop, we insert 1 at the beginning to handle the all 9 cases. This solution is clean, readable, and efficient. Let us try run the algorithm with the input 1, 9, 9. Starting from the last digit, 9 becomes 0 and we carry forward. The next 9 also becomes 0. Finally, we reach the digit 1, which is less than 9, so we increment it to 2 and stop. The final array is 2, 0, 0. The time complexity of this algorithm is big of n, where n is the number of digits, because we may traverse the array once in the worst case. The space complexity is big of 1, since all operations are done in place, except for the possible insertion of a single digit. This makes the solution optimal for the given constraints. This problem demonstrates how basic arithmetic concepts apply to array manipulation. It teaches careful handling of carry, clean traversal logic, and attention to edge cases. Despite being labeled easy, it is a very common interview question and an excellent problem for building foundational skills. That concludes our explanation of the problem plus 1. Thank you for watching and feel free to revisit the examples or code for deeper understanding.